Okay, in today's lecture, we're going to begin our Chapter 3 material on functions and graphs. And we're only going to cover the first few sections of this chapter because it's primarily a review of some topics that you've seen in the prerequisite course 1053, or maybe one of your high school pre-calculus courses or algebra courses. So we're going to move through the first several sections of this Chapter 3 material quickly, since it is a review, and then we'll move to our Chapter 11 material, where we'll jump into calculus. So in this first section of Chapter 3, we're going to talk about functions, which are sort of the building blocks for calculus. So let's start by defining what is a function. Well, a function is defined as a rule that assigns to each element x in some set A exactly one element, which is denoted as f of x, in a set B. So visually, we can think about if we have two sets, let's say sets A and B, for any element in this first set A, a function is some rule, which we will denote as f, which takes the element x and it assigns it a unique value, which is denoted as f of x, in this other set B. Now it does this for multiple elements. Let's say we took another element in the set capital A, maybe call it lowercase a. The function f takes that element and assigns it a unique value in the set B, which we would call f of a. Or for general points, let's say we have some other point, we could call it y, and the function f takes that element y and assigns it a unique value in the set B, which we could call f of y. Now, when we talk about functions, this set A, the first set that we're taking elements of, is called the domain of the function. So it's the set of all possible input values of our function, x, a, y, so on. And the set of values, f of x, where x is chosen to be an element of the set A, is called the range of the function. So here we're taking points in a set A, which is called the domain of the function, and the set of values that are being assigned by this function is called the range of that function. Now, throughout our course, we will be using the convention that the domain of a function, f, is the largest set of real numbers, so real numbered inputs, x, such that the output of our function, which is f of x, is also a real number. So we're only considering real inputs such that the value of our function would be defined as a real number. So having said that, let's look at the following example where we're given a function and we are asked to find the domain of that function. So in part A, we have a function g of x. So we might use variables other than f to denote functions. In this case, we use g of x. And it's defined as the square root of 16 minus x. Now we know in order for the square root of a number to be defined as a real number, we have to be taking the square root of a non-negative number. That is, we cannot take the square root of a negative number, or else we're introducing imaginary or complex numbers. So in order for this function g of x to be defined as a real number, I need the expression that I'm taking the square root of, which was 16 minus x, and I need to make sure that it is non-negative, that is greater than or equal to 0. So solving this inequality for x, we have 16 has to be greater than or equal to x. Simply add x to both sides. So the domain of this function would be the set of all values x such that x is less than or equal to 16. So we could write our answer in this form as an inequality, or we could say that our domain would be some subset of the real line. So recall from your prerequisite courses, if we wanted to write this in interval notation, well, we're looking at the set of all values which are less than or equal to 16. So as an interval, we could take all of the values of x from negative infinity to positive 16, including positive 16. So we could also write our answer using this interval notation if we prefer. But either answer is acceptable here. Now in part B, we have the function f of x, which is defined as 1 over x times x plus 1. And we know in order for this function to be defined as a real number, our denominator can't be 0. We cannot have division by 0, otherwise our function would be undefined. So in order for the function in part B to be defined, we would have to take our denominator for this fraction, which is x times x plus 1, and make sure that it is not equal to 0. Now, if x times x plus 1 can't be 0, that means that neither of these two factors, x nor x plus 1, can equal 0. So we must have x not equal to 0 and x plus 1 not equal to 0, which means that x cannot equal to negative 1. So here we could write our answer in that way. X cannot be equal to 0 or negative 1. Or if we want to write this using the interval notation, well, we could take all real numbers except 0 and negative 1. So we could take everything from negative infinity to negative 1, or from negative 1 to 0, or from 0 to infinity. So recall here that this little u notation is a union symbol, and this is read as the word or. We can take values of x that lie within any of these three intervals. That is, all real numbers except 0 and negative 1. Now in our last part of this example, part C, we have a function g of x, which is defined as the square root of x plus 1 divided by x squared minus x minus 6. So here there's a couple of things we need to watch out for. In order for our numerator to be defined, we cannot be taking the square root of a negative number. So we need the expression under the square root, that is x plus 1, to be non-negative, that is greater than or equal to 0. And I can't have division by 0, so my denominator, which is x squared minus x minus 6, cannot be equal to 0. So let's find our conditions on x. Solving this first inequality for x, I find that x has to be greater than or equal to negative 1 if I subtract 1 from both sides. And at the same time, in order for my denominator to be non-zero, I need to solve for x. So let's see if we can factor this expression. The quadratic on the left-hand side can be rewritten as x plus 2 times x minus 3. So we cannot have that value equal to 0. So now we have x must be greater than or equal to negative 1. And in order for this product to be not equal to 0, neither factor can equal 0. So x could not equal to -2 or +3. So we could write our answer in this way. We need x to be greater than or equal to -1 and not equal to -2 or 3. Or if we want to write this using interval notation, we could say that our domain consists of all values of x, which have to be greater than or equal to -1. So -1 is the smallest value that I could take, up through the value of 3. Everything between -1 and 3 would be valid, but I cannot equal to 3. Or I could take everything that's greater than the value 3. That is everything from 3 to infinity. So we would have the following expression for the domain of this function. Okay. Now, to work a little bit with functions, we're often going to be asked to evaluate a function at some specific number. So let's look at an example of this. Let's suppose that the function f of x is defined as 5 times x squared minus 6x plus 4. And for this function, we're asked to find each of the following outputs. So in part A, we're asked for the value of f of 1. So to find it, we take as our input value x, the number 1, and we're going to replace x in the definition of our function with whatever value we were given, in this case, 1. So here, the value of our function will be 5 times 1 squared minus 6 times 1 plus 4. So let's simplify. We have 5 times 1 squared is 1, minus 6 times 1 is 6, and then plus 4. So combining these terms, we have 5 minus 6 is -1, plus 4 leaves us with 3. Now in part B, we're asked for the value f of 3, so similarly, we're going to take our rule for the function f of x and substitute x equals 3 into the rule for that function. So let's see what we have here. We would have 5 times 3 squared minus 6 times 3 plus 4. So simplifying, we have 5 times 3 squared is 9, minus 6 times 3 is 18, plus 4. And expanding our 5 times 9 is 45, minus 18 plus 4. So that leaves us with 49 minus 18, which is 31. All right. Now in part C, we are asked to find f of 1 plus f of 3. Now in parts A and parts B, we've already found f of 1 and f of 3, and now we're just taking the sum of those values. So we found f of 1 was equal to 3 using part A, and then we're adding f of 3, which we just found to be 31 in part B. So the sum of those values is 34. So using our earlier work, we can find the value of the sum of those functions. Now in part D, we're asked for f of 1 plus 3. Now that is the same as f of 4. So inside our parentheses here, we can take the sum of our 1 and 3. We're left with 4. And we want the value of our function at x equals 4. So let's plug in 4 for the value of x. And we have 5 times 4 squared minus 6 times 4 plus 4. So simplifying, we have 5 times 4 squared, which is 16, minus 6 times 4 is 24, plus 4. So simplifying a bit further, well, we have 5 times 16 is 80, minus 24, plus 4. So 84 minus 24 leaves us with 60. Okay. Now what we'll sometimes be doing in this course is not plugging in a specific number for the variable x, but maybe plugging in a different variable. So in this next example, part E, we're asked for the value f of k. Now here, f of k means that we're taking the expression for f of x and substituting k in place of x. So that would give us 5 times k squared minus 6 times k plus 4. So we would have the exact expression for f of x, but with x replaced by k. And in part F, we've got something similar. We're asked for f of negative m. So we're replacing the values of x in our function with negative m, and that gives us 5 times negative m squared minus 6 times negative m plus 4. So let's see what we have. We've got a 5 times, if we take the square of negative m, that's the same as m squared. Remember, when you square a negative number, it's the same as the square of that positive number. And then our negative 6 times negative m, well, the product of two negatives gives me a positive 6m, and then plus my constant 4. So we would have the following expression for f of negative m. All right. Now, one other thing to point out in this example is a common mistake that students will make where in part D, we were asked to find f of 1 plus 3, and students sometimes think, well, that would be the same as f of 1 plus f of 3. They think you could like distribute that f into our function. But remember, this notation is not multiplication of numbers. It's a function f acting on a number, not multiplication. So notice that our answers for part C, where we have f of 1 plus f of 3, and part D, which was f of 1 plus 3, are two different numbers. We had 34 and 60 for these values. So an important note here is that this is not the same as f of 1 plus f of 3. So keep that in mind as we're moving through this course. So let's look at some other examples. This next example illustrates something that we'll be looking at a lot in chapter 11. So here we have a function f of x defined as x squared plus 4x minus 3. And we're asked to find the following outputs. So in part A, we're asked for f of x plus h. So again, all that means is that we're taking our definition for f of x, and I'm replacing the values of x with x plus h. So let's see what we have here. Using the definition of the function, we'll have, instead of x squared, x plus h being squared, then plus 4 times, instead of x, we're taking x plus h, and then minus 3. Now we could leave it in this form, but we'll see in the next couple of parts in this example and later in chapter 11 that it's useful to simplify this expression. So let's write this out. Our first term, x plus h squared, Well, that's the same as x plus h times itself. And then we have a plus 4 times x plus h minus 3. So let's keep simplifying. The product of x plus h with itself, we can expand as follows. So we would first take the product of our first two factors, that is x times itself. So we would have x squared. Then we take the product of the outer two factors, that is x times h. So we have plus x times h, plus we would then take the product of the inner two factors, that is h with x. So we have h times x, and then plus the product of the last two terms, h with itself, would leave us an h squared. Now moving to our next term, 4 times x plus h. If we take this 4 and we distribute it to each term, we are left with 4 times x plus 4 times h minus 3. So in our last step here, let's keep combining like terms. So we have an x squared plus, now let's look at these next two terms. We have x times h plus h times x. Now remember that the order in which we multiply numbers doesn't matter. X times h and h times x are the exact same thing. So if I'm adding those two values to each other, I have 2 times xh plus my next term was h squared plus 4x plus 4h minus 3. So finally, by expanding and grouping like terms, we have the following expression. So let's look at part B. In part B, we are asked to find f of x plus h minus f of x. So this first term is what we just found. Let's write it out. From part A, we found f of x plus h to be x squared plus 2xh plus h squared plus 4x plus 4h minus 3, and then we're subtracting the function f of x. Now f of x, remember, was our original function up here, x squared plus 4x minus 3. And we're subtracting that entire quantity, x squared plus 4x minus 3. So let's see what we're left with when we combine like terms. So here we're going to have an x squared and then minus x squared. So that x squared and minus x squared term will cancel. And let's see what else cancels. We have a 4x, and then I'm subtracting a 4x on the end. So that plus minus 4x will cancel. And lastly, I had a negative 3, and then I'm subtracting a negative 3, or equivalently adding 3. So the plus minus 3 will cancel. And so let's look at the terms that we're left with. We have 2xh plus h squared plus 4h. All right. Now in our last part of this example, we are asked to find the value of f of x plus h minus f of x. So that is what we just found in part B, was that difference. And then we're supposed to divide the whole thing by h. So let's take a look at this. Using what we just found in part B, our numerator is 2xh plus h squared plus 4h. and then we're dividing the whole thing by h. Now recall that we can split this quotient, which involves sums in our numerator, as the sum of smaller fractions. So we could write this as 2xh over h plus h squared over h plus 4h over h. So simplifying, well, in our first term, we can cancel a factor of h on top and bottom. In our second term, I can cancel 1 power of h on top and bottom. That leaves me with 1 power of h in the numerator. And for the last term, we can cancel that 1 factor of h on top and bottom. And we're left with 2x plus h to the first plus 4. Now another way to see that, if you prefer, is to first, from the numerator of this fraction, factor out an h, which would leave you with 2x plus h plus 4, and then divide the whole thing through by h. So again, you could cancel your 1 factor of h on the top and bottom, and you're left with 2x plus h plus 4. So either approach you want to use there is perfectly fine. So the quantity that we were calculating in this example, which was f of x plus h minus f of x all over h, is sometimes referred to as the difference quotient of the function f. And we're going to see that these difference quotients for functions are important in the study of calculus. We'll see that when we start into our chapter 11 material. So being able to calculate these expressions in parts A, B, and C will be very useful a bit later in the course. All right. Now, this is a course in business calculus, so we will be considering some applications in business, economics, finance throughout the course. So to introduce some application that involves functions in Chapter 3, we're given the following problem. So here we're told the closing stock price of the American Express Company for the years 2013 to 2015 can be approximated by the following function. F of x is defined as follows. So we see here it involves some messy decimals, this function, and in general, when we're working with problems in finance, business, economics, usually the numbers don't work out particularly nice for real-world applications. So in some of these problems we'll consider throughout the course, it's useful to make use of a calculator to simplify some of your computations. Now this function is giving us the closing stock price where the value x that we're inputting to this function corresponds to a specific time. Now x equals 13, we're told, corresponds to the start of the year 2013. So for this setup, we're asked to find the following functional values and explain what our answers mean in practical terms. So in part A, we are asked for f of 13. So just like with our earlier examples, I want to replace x by 13 in the definition of our function. And we have negative 15.27 times 13 squared, which is 169. Then plus our 438.5 times x, which we're taking to be 13 here. And then minus our 3061 on the end. So at this stage, it becomes useful to make use of a calculator. It's a little tedious to multiply 169 by negative 15.27 by hand. It can be done, but much simpler to make use of a calculator here. So that first product leaves us with a negative 2,580.63, then plus our 438.5 times 13 gives us 5,700.5, and then we're subtracting 3,061 from the end. So again, using a calculator to combine these terms, we're left with a value of 58.87. So we found the value of our function. Let's think about what this represents in practical terms. So we were told in the problem statement that the value x equals 13 corresponds to the start of the year 2013, and f of x, the function, represents the closing stock price of the American Express Company at that time. So we could say something along the following lines. The closing stock price at the start of 2013, that is when x equals 13, is the value of our function, which we found to be 58.87. So here, closing stock price would be 58.87. Here we weren't given a unit. It said closing stock price. We're assuming it's in dollars here. It might be, say, hundreds of dollars, thousands of dollars. We weren't told that in the problem statement, so we'll assume it's just in dollars here. Now in part B, we're asked for f of 14. So same sort of procedure. We're going to replace x by 14 in the definition of our function. So again, we have negative 15.27 times 14 squared, which is 196, plus 438.5 times x, which we're taking as 14. And then we're subtracting 3,061. So making use of a calculator to simplify our computations, we have negative 2,992.92 plus 6,139 minus our 3,061. So this simplifies to 85.08. So let's think about what this means in terms of practical purposes. So here, our value of x is now 14. If the value x equals 13 corresponded to the start of the year 2013, then x equals 14 will correspond to the time or the beginning of the year 2014. So our interpretation would be something like the following. The closing stock price at the start of the year 2014 is $85.08. All right. And in part C, we're asked for f of 15 with a practical interpretation. So again, we would have negative 15.27 times x squared. So here 15 squared is 225 plus 438.5 times x, which was 15, minus 3,061. So again, making use of a calculator to simplify, we have negative 3,435.75 plus 6,577.5 minus our 3,061. So this leaves us with 80.75, and our interpretation would be similar to parts A and B. We would say the closing stock price at the start of 2015 is $80.75. Okay, so a little application towards business here, or economics. We see that functions can be used to represent, say, stock prices as they change over time. So evaluating these functions can give us the stock price at a particular time. Now, in the next part of this section, we'll start talking about functions which involve multiple rules or multi-part rules. And these sorts of functions are called piecewise defined functions, or sometimes simply piecewise functions. So recall that a piecewise defined function or piecewise function is some function whose rule is defined in parts. So as an example, we have the following piecewise function, whose definition, f of x, is given by the following. F of x is defined as 4 minus 2x if x is less than or equal to 2. It's defined as 5 if x is between 2 and 4. And it's defined as x squared if x is greater than or equal to 4. So we're asked to find each of the following outputs for this function. So starting with part A, we're looking at f of 0. So to evaluate a piecewise defined function, we need to know which part of the rule we're making use of. So to determine that, we look at our input. Here, x is 0, which is certainly less than or equal to 2. So we're going to make use of our first definition for f of x, which is f of x is 4 minus 2 times the value of x, which is 0 in this case. So we've got 4 minus 0, which leaves us with a value of 4. Now in part B, we're asked to find f of 2. So the value of x that we're interested in is x equals 2. And looking at the definition of our function, if x is less than or equal to 2, we're still going to use the first definition. That is 4 minus 2 times x. So we have 4 minus 2 times the value of x, which was 2. So this leaves us with 4 minus 4, or 0. Now in part C, we are asked for f of 3. So the value of x here is 3, which lies between 2 and 4. So here we're going to use the second definition of our function, which is the constant 5. Regardless of what x is, as long as x is between 2 and 4, the value of our function is equal to 5. Now for part D, we have f of 4. So if x is equal to 4, we're now moving to our last definition where x is greater than or equal to 4. And the function is defined as x squared. So if x is 4, we have 4 squared, or 16 for the value of our function. And in our last example, we have f of 7. So the value of x is 7, which is certainly greater than or equal to 4. So we're using our last definition where we take the value of x squared. So here 7 squared leaves us with 49. All right. So in this next example, let's consider one practical application of a piecewise defined function. So a typical example in, say, business or economics is in the tax rate or income tax rate, depending on an income bracket. So as an example of this, Mississippi state income tax for a single person in 2017 was determined by the following rule or function. So T of X, their income tax, was a function of X, where we're told X is the person's taxable income. And we see that the taxable income was 0.03x, so that is 3% of their taxable income, if the income was between 0 and 5,000. It's equal to 150 plus 4% of the person's salary over $5,000, or over 5,000 if the value of X is between 5,000 and 10,000. And lastly, it's defined as 350 plus 5% of their income over 10,000 if X is over 10,000. So here we're asked to find some values of this function and interpret our answer. So in part A, we're asked for T of 100. So here, if the value of X is 100, then we're working with the first definition of our function, where X is between 0 and 5,000. Now the definition of our function there is 0.03 times 100, which leaves us with 3. So an interpretation of this, we could say, the income tax for a single person earning 100, let's say $100, would be $3. So for a person earning $100 in taxable income, the income tax is $3. All right. Now in part B, we're asked for T of 7,000. So now here, where our X value is 7,000, we're moving to the second definition of our function, where X lies between 5 and 10,000. So using that second definition, we have 150 plus 0.04 times X, which is 7,000 in this case, minus 5,000. So simplifying, we have 150 plus 0.04 times 7,000 minus 5,000 is 2,000. So we then have 150 plus our 0.04 times 2,000 gives us 80. So taking the sum, we're left with 230. So our interpretation would be, for a person earning $7,000, their income tax is $230, or $230. Okay. So in our last example, we are asked for the value of T of 120,000. So in this last example, our value of X is 120,000. So we're using this last definition of our function where X is greater than 10,000. So here, our function is defined as 350 plus 0.05 times X, which was 120,000, minus 10,000. So simplifying, we are left with 350 plus 0.05 times our 120,000 minus 10,000, leaves us 110,000. And so we are left with 5,850 for our value. So the interpretation of this would be for a person who is earning $120,000, their income tax would be $5,850. Okay. So we start to see some applications of these piecewise defined functions in that people who have a higher income bracket are taxed a larger percentage of their income. Now, in this last example for functions, we'll consider determining cost, revenue, or profit associated with operating some business. So in this first example, we are told an aluminum can factory has daily fixed costs of $120,000 per day. Now, fixed costs means just the cost for, say, opening the plant, providing electricity to it, basic maintenance, without producing any units. Just basic cost of operating the plant without production would be $120,000 per day. Now, additionally, we're told it costs $0.03 or 3 cents to produce each can. Moreover, we're told that they sell a can to a soda manufacturer for $0.05 or 5 cents per can. So in part A, we are asked to find a cost function, C of x, that gives the total daily cost for producing X cans. Now, in general, our cost can be thought of as the sum of our fixed cost, that is the cost regardless of whether we're producing anything, and our variable costs, where variable costs refer to the cost, the varying cost of producing a certain number of items, in this case aluminum cans. So using some notation here, our cost function, we could say, is C of x. It depends on the number of cans x we're producing. And it's defined as the sum of our fixed costs, which were $120,000, and the variable costs. Now, we were told here that it costs $0.03 per can. So we have our $0.03, and we're multiplying by x the number of cans that we produce. So this would be a cost function describing the cost of producing X aluminum cans per day. Now in part B, we're asked to find a revenue function, R of x, that gives the daily revenue from selling X aluminum cans. So if we produce X cans and we're able to sell all of them, we want to know what would our revenue be. So in general, revenue can be thought of as the revenue per can or per item times the cost that you're, or times the number of cans which you're selling. So that is how much money do you make off of each can. We're going to multiply that by the number of cans that were sold. So here R of x for revenue. So our revenue per can is 0.05. We're told we can sell them to a soda manufacturer for that amount. And the number of cans sold was X. So here our revenue function is defined as the price per can times the number of cans sold. All right. And then lastly, in part C, we're asked to find the profit function, P of x, that gives the daily profit from producing and selling X aluminum cans. Now, in general, profit can be thought of as our revenue minus our cost. That is how much money we have coming in minus how much money we're spending. So profit, if we think of it as a function, P of x, is equal to revenue, which was R of x, minus our cost, which was C of x. So our profit function, P of x, is equal to the revenue, which we found to be 0.05x, minus the cost function, which we found to be 120,000, plus 0.03x. So combining like terms, let's see what we're left with. We have 0.05x, and we're subtracting 0.03x, which gives us 0.02x, and then we're still subtracting that 120,000. All right. So that concludes our first section of Chapter 3, a little review on the definition of functions, how to find the domain of a function, and some applications of functions or piecewise functions in business